Okay, now today, I won't review what we did last time because it was just kind of, I like to review a lot, but last time was too technical. Just to remind you, is that you run into these transcendental equations. I'll give you an example. As undergrads, everything's a line, right? When you take data, it's an exponential decay, but you take the natural log and it's a line. You either fit lines or you make them lines. By your exponential decays, take the natural log and now it's a line. Everything's a freaking line. Well, in grad school, not everything can be linearized, like a Gaussian peak, right? So on my little MATLAB tutorial thing I gave you a link to, or sent it to you, I don't remember. You can't linearize this, right? So how do you fit this, right? So these are the kinds of things that you got to get used to. And the fact that you have in that last example an equation equal to a function of an equation, an energy equal to the function of energy, you can no longer just say E is equal to just some constants that you plug in from your model. That you actually aren't going to see this often anymore. So you got to learn to roll with this, right? And of course, as I mentioned, what I like to do is using the computer methods that I'm showing you. I subtract the two and find where it's zero, and computer algorithms are really good at that. Actually, what sometimes they do, some computer algorithms are good at minimizing functions. So what I would do is I'd find the minimum of this. See what I mean? Why did I square it? Why didn't I just find the minimum of this? Huh? Right, it could be negative. This could be negative, so what the computer would do is just make this as negative as possible. A square can never be negative. So anyway, tricks. These are the kind of tricks that you really should know, because if you get good at computer this and that, you're going to be a better grad student, you're going to have better data, you're going to get results faster, you'll graduate sooner. So anyway, that's my philosophy on this stuff. All right, now, as we advance further, I'm still going to do flat potential surfaces today and Wednesday, and then on Friday as well, but we're going to do three-dimensional. But we're, more and more we're leading undergrad level. Like last time, that derivation, that was a freaking nightmare, right? We don't do that. I don't do that for undergrad. At the same time, it is a flat potential. We're going to do another problem. It's going to seem stupid at first. It's kind of cool though. And then we're going to take the stupid model and make it more complicated, and then it's going to be really cool. Okay, so here's the model system. So it's a flat potential at x equals 0. I'm going to have a potential energy that's infinitely large. Now just post at x equals 0. Now, an infinitely large potential can't be penetrated. Wave function has to be 0. So I'm going to make it infinitely thin. Okay. Now how do you do that? What's a function that's infinitely large yet infinitely thin? Huh? Yeah, delta function. So we're gonna have a delta function. Now I know how to put x minus 0, right? Delta function centered at 0 is x minus 0, and that's just x. So I'm going to make the potential a delta function. Now this is kind of a cool math exercise. The solution will we actually use the Schrodinger equation to solve it. It's one of the few times you actually use the Schrodinger equation to solve the Schrodinger equation. And true, but unbelievably annoying, but true. The result will be like, well, whatever. But then I'm going to do something with it that's going to make it one of the cooler problems you've ever seen. Now what we're trying to do is look at scattering. So any kind of scattering means that I'm going to have an A wave. Here's an A wave. It'll scatter off, so there's a B wave. And then, of course, there'll be some transmitted C wave. So the see, we call those scattered waves, whether they were scattered forward or backward. Normally scattering would be more complicated, but in one dimension you can either go left or right, so it's kind of simplified, right? So that's all fine and good. Now, we've already done some stuff like this, but what I'm going to show you with this, when I complicate the model, is going to be a resonance, a resonant behavior. So as for what that means, I'll show in a minute when I get to the more complex model. The more complex model will have two delta functions, by the way. Okay. Now, for stupid reasons that are just going to make our lives easier, I'm actually going to multiply this by some constants, h bar squared over m. I'm doing that because in the derivation, it doesn't matter, it's infinite. So a number times infinity is still infinity. I'm doing this because in the derivation, it just makes it easier. It doesn't matter. It doesn't need to be there. It just makes things easier. So why would I not want them there? Okay, so the setup again, our A wave is going to hit an infinitely high yet infinitely thin barrier, and it kind of messes with you, right? Like, infinitely high is bad, but if it's infinitely thin, it's not really there. But it is infinitely high. But it's straight right over and over and over again. All right, it does matter. So how do you solve it? Again, this is one that you actually use the Schrodinger equation for. First, let's all right, wave function one, region 1, region 2. Wave functions are tell you what, a, let's make it equal to 1, e to the plus I k x plus b e to the minus I k x. Now, what's kind of cool about this is that region 2, we just have a right moving wave. The k's are the same. K's are the same because they're both regions don't have potential energy. So to some degree, it starts out kind of easier. I kind of hate all this K1, K2 business myself. All right, now, so we're going to solve it with the Schrodinger equation. And so that's kind of neat. Now, I'm sorry, let's first, of course, start with our stipulations. One is continuous at x equals 0. And so that ends up being, 1 times 1 plus b e to the minus 0 is 1 is equal to c e to the 0 is c. So that it ends up being 1 plus b plus c. So we're also, sorry, I should back up a bit. Remember, I keep saying that these models serve a purpose. There's no quantized energy, so we're not trying to find k. We're not going to find a transcendental equation for k like I was blabbering about before. We're just looking for a, b, and c, or a is 1. Okay. Of course, we're looking for boundary conditions, right? How many unknowns do we have? We better have as many boundary conditions, right? So that's what I'm doing. Should have mentioned that before. So let's do smooth. Smooth. Actually, we have a problem with smooth. Did I misspell that? Anyway, we have a problem with smooth. Okay, so this is the one thing I don't like so much about this. A delta function can blow the smooth criterion. So on your homework, you're going to do a similar problem, except the delta function is negative. So the wave functions are not smooth. You're going to need to solve it the way I'm solving it. So I know that we keep saying smooth and continuous. This type of potential will blow that. Of course, it's also completely unrealistic, right? Again, we're just trying to learn some lessons here. Okay, so we're going to forget smooth because this is the one time that actually won't be applicable. What we're going to use is, as I mentioned before, we use the Schrodinger equation to solve this thing. Because well, that's just how you do it, I guess. I don't know how to describe it as massive. Here's our kinetic energy, here's our potential energy. The total energy, and therefore, actually, if you don't mind if I just do this, well, no, I will. Yeah, I'm tempted just to, I try never to do this, I'm tempted to just wipe out what I just wrote. and just say, oh, look, it's, you see what I mean? Because I want to do this. I want to do that right there, but it's hard for you to follow that in your notes. Okay, then what I do is I'm going to factor the h squared squared over 2m. So you see why I put that in there. It doesn't need to be there. Infinity times this is still infinity. I did that because, just the next step, because what you then get is, I'm just going to isolate this double derivative. So I got rid of the constants. And so then I've got my k minus 2me over h part squared. That damn thing shows up all the time. Bracket minus, plus 2 gamma. Oh, sorry. I did mess up. I messed up. Okay, so gamma's purpose is to give it magnitude. So, all right, so the h squared squared over 2m, sorry about that. The h squared squared over 2m was there, just so I could get rid of it here. Again, it doesn't, I can keep it, it doesn't matter. But because it's gone, I need to have something remain to give it a magnitude, even though the magnitude is infinity. You'll see what happens here in a bit. It's basically, the problem is highly engineered. This is a highly engineered problem. To give a lesson, but to try to make it as easy as possible, it helps if I've got it right. Okay, so there you go. Sorry about that. Anyway, that's correct. This, okay, minus, plus, and of course this is k. Where's that 2k? So that's just k, right? Now I'm hoping that you're familiar enough with k that doesn't blow your mind. Okay, so next step. Okay, so I am going to just write this again. Let's write this thing out again. Tell you what. Let's see what I want to do here. Yeah, I'm going to write this a little bit easier. Okay. Now, this is where this gets kind of funky. What I'm going to do, integrate it. Okay. Games with calc that you've probably never seen before. You can do stuff like this. What I can do is integrate it over an impossibly narrow region at x equals 0. I know what I do is, you're gonna run into this a lot, by the way. You see integrals like this all the time with this more advanced maths. All it means is that we're integrating that thing arbitrarily close to the origin. Now, as for how you deal with that, I'll show you right now. Okay. So what do you do? Okay. Integrating. I better have a D. Units weren't correct. Actually, that's how I do that. Something was wrong. Okay. So, integrating a double derivative just needs to be a single derivative, and then I would have the upper bound minus the lower bound. Okay. Now, if I integrate the left side, you better integrate the right side. So let's do that. And I'm going to distribute the wave function. Okay, so I know that's a lot to hack. this is the part that's bad, right? But it's not terribly bad because derivative of the wave function at epsilon. All right, notice I've got the wave function because of our earlier demonstration of three waves, right? We oddly did solve the Schrödinger equation, not quite for this problem, but anyway, three waves. So I know what the derivatives are. It helps that epsilon is 0. Now, as for what it means right and left, it means that this guy, that's to the right. To the right of 0 is region 2. So I'm going to use region 2's wave function here and correspondingly region 1. Right? So that's how you deal with it. Right? So that's, as much as this was looking a little cross-eyed, it's really not that bad at all. Okay. The derivative to the right, of course, is going to bring down ik c e to the ultimately epsilon is arbitrarily approaching 0. So you know what? E to the 0 is 1. Right. This ends up being really, really quite simple, right? Okay. Minus, then the same deal to the left. I can factor out with ik. A is 1. The derivative brings down minus ik, but I factored already. And let me make sure. Yeah, and then e to the blah, blah, blah is still 1. Right? So, not bad. Turns out not to be bad. Okay, then this side, you know, as an undergrad, if you saw this, you would throw up with you. You'd throw up in anger. What is this? All right, so these are constants, so 2 gamma, whatever gamma is, that's irrelevant. Psi of x, delta function x. Remember, I told you delta functions are everywhere. What does it do? Omega. It's a constant. Right, what it does is, all right, delta functions, as much as it looks like you're in some math land that will blow your head off, delta functions are awesome because they kill integrals. So think of this integral as like you're moving along the surface, and everything is 0. So there's nothing to integrate. Only when you hit x equals, in this case, 0, only then does this thing allow anything to happen. But over such a narrow region, that all you end up with is wave function at 0. But I know what that is. That's now heads up on one thing. It actually, I can use the left or right half for this part. Now here, derivative on the right minus derivative on the left, you have to do it that way. But as for this one, by the way, it doesn't matter whether you were to use c, which is the right-hand wave function, or 1 plus b, which is the left. It doesn't matter which one you pick. We're going to do some more algebra, and it just affects how the algebra is done, whether it's more or less steps. To be honest, this really takes less steps. That's why I did it this way. Okay. Again, if you plug in, you can see why, right? Because I have, anyway, it's easier. All right. Excuse me, what about this one? No delta function to save you. Limit of epsilon goes to 0, by the way. That's actually solved. If you're looking at this trying to figure it out, you won't be able to unless you take that into account. That limit applies across the board. I should have written it in front of every integral, to be honest. Notice it didn't do anything here, but here it very much does. What do you think? What? 0? Huh?
It's a k squared c.
No, there's 0. All right, integrals. When you first learn to do integrals, they're the area under a curve. What is the area under an infinitely thin curve without a delta function to rescue you? 0. Right, it's because it's an infinitely thin all right, another way to think of it is dx, the width is 0. 0 times anything is 0. Very good. That's another way to think about it. Okay, so cool. All right. Well, that's actually it. Here, you can let me. So you know 1 plus b is equal to c. That came from the first stipulation. So let me just do algebra. I don't really want to do all the algebra. That's kind of stupid, right? So do a bunch of algebra. You're going to have to do basically this on your homework. It's a very similar problem that you have. It ends up being base gamma, whatever that is, ik plus gamma. Okay, now, personally this would freak me out because I see the letter I. I don't like the letter I. However, b squared is the reflectance, which is b star b. Now, again, on your homework, you might want to work that out. But I've been doing this long enough that I just know that it's the absolute value. So the absolute value on top would be gamma squared, and on bottom it's k squared plus gamma squared. Now that's just, you can think of these like vectors in different directions, where that's x and that's y. That's why when I see these, it's just unbelievably easy. It's the real and the imaginary squared. There's no cross talk. You know, when you see squares, you're like, oh, there's I, k, gamma minus I, k, gamma, or is it no, is it 2 I, k, gamma? You know, you get all those FOIL things in your head. They actually disappear because they're basically like different directions, so it's actually easier. Okay, so then, and then now C is 1 plus that, which is the transmission. Did I write this down? IK over. So again, I'm not going to do all the bloody maths. Sorry, I'm not using the board super well. And then of course this is k squared over k squared plus gamma squared. There we go. Yeah, okay. So what that means is, now again, I told you this problem is stupid, it's boring. What you have is, I'm going to plot k. And of course, k can be 0, and that corresponds, remember, this is really square root of n. So this is really energy. And somewhere I have gamma, so gamma, just looking for any expression. Gamma, so when I see this term, and this term have to have the same units. Delta functions, I'm not sure if delta functions have units. Do delta functions have units? I don't think so. So that means that gamma has to have the same unit as k squared. So anyway, so maybe this is square root of gamma. So I can't plot them unless they have the same units. Anyway, I'm not particularly worried about that. The point of this is that you find, okay, 100% reflectance. So this is percent R. And then, of course, the transmission will mirror that. It's just a mirror image if you do that. Okay, so we're seeing, so I know it seems silly at first because it's basically the step potential, just kind of slightly harder to solve it, but definitely involves a little bit more difficult mathematics to solve it. So maybe it's like not a little harder, maybe it's a lot harder. That's why we just did it. But and you notice you get kind of a similar result. It's kind of neat that you can get reflectance or transmittance a little bit before the barrier. And if you recall, the finite barrier, the reflectance was 100% until you hit the barrier. Here, you have a little bit of leeway. So, anyway, whatever this does, it's doing it right now. And whatever you get out of it, you've gotten it. And I told you that as much as, and I hope this part was fun. All right, but we're done with it. So kind of like, I remember I was telling you at the beginning of the lecture, that I would do this problem and you'd be like, yeah, all right. But now I'm going to make it cool. It's going to be a lot harder, but I'm going to make it cool. And here's how I do that. Now I've got flat barrier still, delta function at x equals 0, and now I'm going to add another one. My deltas are not. It's not right. Looks like a weird alpha. X equals a. Now I got two delta functions. Okay, now why am I doing this? I'm doing this because this is your first foray into resonant behavior. What's going to happen is some waves bounce, especially if they have low energy. Some waves will shoot right through. And some get trapped. Some get trapped inside of you. And you can see that different behavior all happening, still a relatively simple model, but you can observe all kinds of behavior. So that things won't go through if they have too low energy is not particularly mind-blowing, but that if things hit this just the right way, they shoot through, and that's a resonance. If they have a little bit more energy, they may be off resonant, and they'll actually get trapped inside. And then if they have more energy, then they'll shoot right through, but then if they have a little bit more energy, they get trapped inside. So you see these undulations in the transmission. Up and down, and up and down. And again, you hit it just right, you shoot through, but if you have more energy, you actually find yourself trapped in here. By the way that works, if a wave shoots right through it, it's because the wave has a node at the barrier. All right, you see that? For the particle to interact with the potential, it has to have amplitude at the potential. The wave function must have magnitude. But if the wavelength is just right, if the wavelength is basically A or half A, it has nodes. So it actually doesn't experience the potential. So it'll shoot right through it. See what I mean? And if the energy gets higher, and not lower, higher, then the wave may actually have amplitude. All right, maybe it goes through this one, but it won't go through that one. It'll hit it. And then it bounces back and gets trapped. Eventually it'll leak through. But anyway, so that's how this is ultimately going to work. Okay, what is unpleasant is solving it. So and now this is several examples on your next homework are like this. We now have 1, 2, 3 regions and 2 boundary conditions. So this is going to suck. Unbelievably. Okay, let's do region 1. A will be 1. So let's do I. And there's still, okay, the saving grace is that there's still only 1K. So minus IKX, okay, region 2. Now here we will have the full complement. Oh, sorry, that's D. There's no reason to say, yeah. See, if it passes through, it might bounce off the back, the second barrier. So now we have 2 waves, and then in region 3, we're back to normal. We'll have just an E wave. All the K's are the same, so that's like the only thing that helps us out at all. And by the way, at one point, I actually, as much as I'm like, oh, just do the algebra on your own. we're going to come to a step where I'm like, you're going to do it on your own with the computer. And that's, again, a big part of the homework. I have to admit, I'm kind of cross-eyed here. I have to, okay. At x equals 0, so we have two sets of boundary conditions. So what I want to do is basically work through all the tediousness, get to a point where you've got all of your boundary conditions, all of your equations with the same number of equations as you have unknowns. And at that point, unfortunately, to be blunt, it's so complicated. I'm not going to sit here, I'm not going to do 5 pages of algebra. Again, it would take 5 pages to do these two barrier problems. It takes about 5 pages of algebra. I'm going to have a computer do that. Screw that. Okay, so at x equals 0, wave function 1, in case you get lost, what the heck I'm even doing? Wave function 1 is equal to wave function 2. So 1 plus, and we're at x equals 0. So thank God we got that going for us. Okay. And let's see, now what? Okay, now what I'm going to do is I'm going to do this. I'm going to do the same thing, but you can see what happens. Derivative on the right minus derivative on the left equals whichever one you're choosing. Okay, so let me just do that. So derivative, and just so you don't get lost, derivative on the left minus derivative on the right. And I will choose a wave function at where I'm going to make that region 1. And again, I do that because I know that the subsequent algebra is a little bit easier. You can do region 2 at x equals 0. You're going to have a little bit more algebra. It's a practical thing. Okay, region 2 is I, K, C. D is the backward wave, so its derivative is minus IK. D e to the 0 is D. Okay, that's this. Then we subtract the right, the left half, sorry. Minus IK. Okay. And again, 2 gamma, 1 plus 3. Okay. So, the big check, the big check. These are what need to go into the computer. So, again, on the homework, I show you in MATLAB. Hey, MATLAB, sim BCD. And it says MATLAB, we're going to be getting some equations where B, C, and D are symbolic. That's what sim means. And then you're going to feed it equation, and then we have 2 more. And then you say, hey, symbolically solve for, who cares about me? Solve for E. And MATLAB does it, right? So that's kind of awesome. You know, what I like doing about this is, the reason I want you to do computers, for one, freaking computers. Number 2, I actually can give you like way harder stuff. If I gave you this problem for homework, and it kind of did, it would take the entire week to do this one problem, but now I can do like 5. So, and that's better for you. So that's what I'm going to tell you. Okay, now at x equals a, this gets a little bit hairier. Now you can see why you need to use a computer. Okay, now there's 2. We do have the continuous. Smooth doesn't work. We do have the continuous. Okay, and that's not that bad. C, E, the IK, we're at position A, positive, plus D, E to the minus IKA is equal to E, which is only positive IKA. Okay, so not that bad. Now, let me show you a trick. Multiply by E to the minus IKA on both sides. This is going to make you a lot less cross. The computer doesn't care. The computer doesn't care, but it's going to make you a lot less cross-eyed. You see why? C plus D e to the minus 2ika is equal to E. Right? Way the heck easier. Way the heck easier. It's the same thing, but easier. Okay. There's a big check mark. There's your third equation. Let's see. How many unknowns do we have? B, C, D, E. 4. Right? It's important. This is how you know. These are the kind of things you got to look out for to make sure that you're not completely off in la la land. 4 equations, because we're not worried about k's. The k's can be anything. So we don't have, it's not a k problem. It's an A, B, C, D, E problem. But I don't worry about A. A is 1. B, C, D, E, 4. 1, 2, 3 check marks, but of course the fourth one, which will do it. This is the second step at x equals A. So we have region to the right, which is actually region 3, minus the derivative to the left of the barrier at A, which is region 2. 2 gamma, take a wave function, and again, I'll take wave function 2. Actually, when I made my notes, I made certain I could sit down and do it. I think I actually even did it on pen and paper. And then I did it on the computer to write your homework. And I found it truly doesn't matter which one you pick. Again, just be faster or slower. Okay, now, unfortunately, this gets a little bit nasty. Sorry, to the right is ike e to the ika. So this is a little bit nastier. Okay, C ik, C e to d ika. Now the thing about derivatives, they always bring down a minus sign. That's coming from that minus sign. So now remember, I keep ballying on and on and on about, oh, you need a computer, oh, you need a computer. You see why? It's this part right here. This is awful looking, but it is just a bunch of algebra. Okay, now do the same trick. In fact, you know, it's like you can factor out letters. You can factor out i's. That's going to make things a lot easier. So what you get is E minus C plus D. So if you do some factoring, it's not quite as bad. Oh, it's a little bit, so I told you you can factor out the IKs. Oh, and God knows, folks, don't think E is energy. Okay. So, not, childlike, a little more complicated, a little easier. Yeah. So 4 equations, 4 unknowns, and you solve for E. Okay, so that sucks, right? Now I'm telling you, how many pages is that? It's actually, you get kind of lost. There's actually, just so you know, use a computer. Number 2, there's actually a matrix method. Remember when you're solving system of equations? You should have done it in 8th grade. Systems of equations, you can use matrices to solve them. Just saying. Right? So the thing about matrices is what they do is they make you work efficiently. I mean, like, okay, I'm going to solve for B, and then I put B into here. Okay, then I can solve for C and D, and then I'll put it in. If you can go backward if you're not careful. Right? So that's the thing that sucks. A matrix will not allow you to go backward. So that's why that's useful. Or use a computer. I use a computer. I think I did it if I can. And again, E is not energy. In fact, when I'm really being careful, I don't use E, I use F. So sorry about that. I need to maybe update my nose. So this is what I got, and maybe you're doing such a similar problem in your homework, you might want to verify that this is the case. Once you write the software to do your homework problem, it's not going to be like hard to modify for this. So yeah, look at that. It's a little bit of a meh. Okay. And I'm almost done. So let me draw it. Let me draw what the results look like. Let's see here. Yeah. Okay, now one thing to note is that, again, one of the things you can do to get yourself wasting time is this by itself is meaningless. Plot the complex absolute value. Be a little careful about how MATLAB, you can have MATLAB calculate the absolute value for you, but there's actually two ways to do it. Sometimes it says real squared plus imaginary squared square root, which is actually not what you want. Sometimes it's just real squared plus imaginary squared. That's what you want. So again, when you look up MATLAB, how to do absolute value of complex numbers, it gives you two ways to do that. That's how they differ. It actually really wouldn't matter which one you picked. I mean, I generally know which one. They actually look about the same. It hardly matters. But anyway, just want you to know that. Okay, now here's how the thing looks. And this is a very typical resonant behavior. You can see that the damnedest thing is, even for finite energy, even if you're well below whatever that gamma, that's kind of the well height, kind of, you know, it's a weird problem. But any energy gets you through to some degree. But then you see these resonances, and this is exactly at 1. And on and on and on and on. Now again, this behavior we observe in the physical sciences all the freaking time. X-rays shooting through atoms. An atom is the barrier, X-rays the X-rays, the wave. You see this behavior in Argonne National Lab, you see it all the time. It actually reports the structure, that this is like what my group does. Lots of groups do this. Savannah, sometimes James and Mary. Hold on a second. I wish I had time to start up the computer, but that thing's not right. Yeah, I've only got 2 minutes left. Okay, so let me show you what it looks like if I did have time to graph it. So when I look at, so what I do is I calculate the wave function squared. So you see why I wanted you to do that on your homework. And then, in fact, that's not considered. Let's look at that. Okay, now the wave function squared for a wave is e to the ix times e to the minus ix, so that's always 1. And then what happens is I plotted a k. So the way I do this is I feed this thing energy, which is in the form of k. And I gave it 1 nanometer, so I had to have mass of an electron, 1 nanometer. Energy is like an EV from 0 to whatever, however far I feel like graphing it. So there's your k. Gamma, I just made up a number. It took me a while to figure out a number that makes it all make sense, but anyway. And then I plotted the wave functions for those k's. This gives me a k. All the other parameters are set. And here's what they look like. The next one. Like that. And I think I screwed that up, but anyway, I think I screwed that up. Particle in a box. The particle in a box states. So now, if you could imagine, if I could keep drawing these waves up, see, I had to do the algebra. You see, the waves happen to have nodes right at the barriers. And these other waves too. So because they have nodes right at the barriers, they look like particle in the box states. I mean, they are particle in the box states. And that's why they can shoot through. And that's why I'm telling you at Argonne, when you go do X-ray stuff, an atom ends up being a potential like this. And so what we see is that sometimes the X-rays are just stopped and you don't get any transmission. And then if you raise the energy up a bit, it just goes right through. So anyway.